Now for the solutions to the quiz at the end of lesson 6.3. So number 1, we have a case where the current is decreasing because the switch has been opened. So the inductor acts to maintain the current, so that is a B. And then we have number 2, the inductor stores its maximum amount of energy once the current is at a maximum, and that is C. And then for number 3, we've got the same length, but we've got 3 times the number of turns per unit length, and that means the inductance is 9 times, so that is E. Now for number 4. We have an inductance of 1.4 millihenries, and we have an area of 1.2 by 10 to the minus 3 square meters. We have a length of 0.052 meters. And the question is, what is the number of turns? Now our equation for inductance is L is mu naught N squared A times L, where N is the number of turns per unit length. So let's make that the subject. So N squared is going to be L over mu naught A times little l, which is the length, which is going to be 1.4 by 10 to the minus 3 henries over 4 pi by 10 to the minus 7 times 1.2 by 10 to the minus 3, which is A, times the length of 0.052, and that gives us 1.785 by 10 to the 7. So that means N, which is the square root of that, is 4225 turns per meter. And so the total number of turns, which is the number of turns per meter times the number of meters, is going to be 220 roughly turns. Now number 5, we have an induction coil and we've got an input voltage of 10 volts and we've got a voltage in the secondary. The output is 20,000 volts. So we have 200 turns in the primary. How many turns are there in the secondary? So we know that the voltage over the secondary over the voltage in the primary is going to be the number in the secondary over the number in the primary, and that voltage ratio is 20,000 over 10, which is 2,000. So that means the number in the secondary is going to be 2,000 times, because it's stepping up, the number in the primary, which is 200, and that is going to be 400,000 turns. So that was number 5. Number 6, we have a car ignition coil and it is storing 70 millijoules of energy. And the spark current from out of the secondary coil is 0.08 amps. So what is the size of the inductance in the secondary coil? Now our equation is that the energy is a half Li squared. So 70 millijoules, which means times 10 to the minus 3, equals a half times L times 0.808 squared. So we have L equals 2 times 70 by 10 to the minus 3 over 0.08 squared. And that gives us that the inductance is 22 henries. Now number 7, we have a solenoid with inductance 3.1 henries, and we then have a current which goes from 15 to 0 amps. So the change in current is minus 15 amps, and the time interval is going to be 75 milliseconds, so 75 by 10 to the minus 3 seconds. Now, the EMF is part A, so EMF is going to be minus L di dt, and that will be minus 3.1 times the change in current, which is minus 15, over 75 by 10 to the minus 3. And that gives us plus 620 volts. And the reason it's a positive is that the change in current was negative, so that supply EMF was decreasing, and so the induced EMF is a positive voltage. And part B, we have, again, energy is a half I squared, which is going to be a half times 3.1 times 15 squared when it was at its maximum, and that is approximately 350 joules. Now, number 8, we have a solenoid and the inductance is 6.3 millihenries, and the resistor has a resistance of 1.2 kilo ohms. Now, we want to know the time for the current to rise to 63%, and that is what the time constant represents. And the time constant for a RL circuit is L over R, which is 6.3 by 10 to the minus 3 over 1.2 by 10 cubed, and that gives us 5.3 by 10 to the minus 6 seconds, or 5.3 microseconds. And finally, number 9, we have a length for our solenoid of 1.2 meters. We have a radius of 2.5 centimeters. We have a number of turns, that is 1200. And we have a permeability of 9.4 for this ferrite, of 9.4 by 10 to the minus 4 henries per meter. So, starting with our equation, we know that inductance is mu here because it's not mu naught, N squared A times L. So the things we have to work out. Let's work out N, which is total number of turns over the length, is 1200 over 1.2. That is 1000 turns per meter. And the next thing we have to work out is the area. So pi r squared, which is pi times 0.025 squared, which is 1.96 by 10 to the minus 3 square meters. So that now gives us an inductance which is 9.4 by 10 to the minus 4 times 1.96 by 10 to the minus 3, which is A, times N squared, which is 1000 squared, times the length, which is 1.2 meters, and all of that together gives us 2.2 henries as the answer for the inductance.